Welcome back to Calculus 1. I'm Dr. Jeff Groh. Today, we're going to talk about the product and the quotient rules. The question is, what happens if you take the derivative of the product of two functions? A lot of students attempt to just multiply the product of the derivatives, but it turns out that doesn't work. Let me illustrate why that doesn't work. Suppose I'm taking the derivative of x times x squared. Well, you know that is equal to the derivative of x cubed, which is 3x squared by the power rule. Does that equal the derivative of x times the derivative of x squared? No. So you may not calculate the derivative of each factor separately. You don't get the same result. We need to figure out what does work. We don't have much to go on other than the definition of the derivative. So here goes. Suppose we're taking the derivative of f of x times g of x. Well, the only thing we should go on is it's the limit as h goes to 0 of f of x plus h g of x plus h minus f of x g of x all over h. What else can we do? Now, there's a little trick to this. In expressions, you can always add 0 or multiply by 1. We've seen that multiplying by 1 trick when we multiplied numerator and denominator by the conjugate of the numerator. Here, we're going to add 0 in a special form. This is going to be a long expression, so I'm going to move it as far over as I can. Equals. The limit as h goes to 0, f of x plus h, g of x plus h. Now here's the trick. F of x, g of x plus h, which is something new that didn't appear above. To maintain equality, I better add it back. And we still have minus f of x, g of x, and it's still all over h. Now, we're going to separate this out a little bit. On the first term, we have a common factor of g of x plus h. I'm going to factor that out on the right. In the next two terms, we have a common factor of f of x. I'll factor that out on the left. Now, when we take the limit, this first factor on the first term tends to f prime of x. The second factor tends to g of x because h is being sent to 0. On the second term, we have f of x, and then the second factor in the limit as h goes to 0 goes to g prime of x. We have what is called the product rule. The theorem is called the product rule, and it goes like this. Here's an abbreviated version. If you take the derivative of f times g, you get f prime g plus f g prime. In a slightly more long-handed version, the derivative of f of x times g of x is the derivative of the first factor times the second factor plus the first factor times the derivative of the second factor. And I want you to remember this in this order. There's a reason for that. In Calculus 3, we have a kind of product called the cross product. And the cross product is not commutative, or even associative for that matter. But in particular, it's not commutative, so it matters which way you write the factors in the product. If you want to get the product rule for the cross product right, the factors have to be in this order. Derivative of the first times the second plus the first times the derivative of the second. Don't switch them around. I know. Multiplication in the present setting is commutative, so it is permissible. I'm just trying to help you out later on in your studies. For example, suppose we're taking the derivative of e to the x sine of x. We'll do this kind of in a long form on this example. You don't need to do all of these steps in your own work. That's going to be the derivative of e to the x times sine of x plus e to the x times the derivative of sine of x. Well, you know that the derivative of e to the x is e to the x. Kind of a remarkable example. Times sine x plus e to the x times the derivative of sine x, which you now know to be cosine x. Let's suppose that f of x is 3x squared plus 2x times 5x plus 7. Now, I could go through all the trouble of foiling this out and then calculating the derivative, or I can calculate the derivative directly. It's the derivative of the first factor times the second factor left alone plus the first factor times the derivative of the second factor. On an exam, if I give you a problem like this, I don't want you to simplify it. I want you to just leave it. I'll assume that you know how to simplify such a trivial expression. Another example, let's suppose y is equal to x e to the x minus e to the x. Let's calculate dy dx, or y prime. Remember that y prime is Newton's notation for the derivative, whereas dy dx is the Leibnizian notation for the derivative. It means the same thing, though. On the first term, since we have the product of two functions, we must use the product rule on that term. We get the derivative of the first times the second plus the first times the derivative of the second, and then minus the derivative of e to the x, which is e to the x. These terms cancel, and we get x e to the x. Another quick example. Suppose that f of x is, say, x squared cosine of x plus 3 sine of x. The first term is a product of two functions, so we must use the product rule here. The derivative of the first times the second left alone plus the first times the derivative of the second, which is minus sine of x. And then in the derivative of the second term, the constant factor of 3 pulls out of the derivative process. We get 3 times the derivative of sine x, but that's just cosine x. And so we're done. Okay, you now know the product rule. I think this is the 4th time I've written this on the whiteboard. You know it's important. You're going to memorize this right now. Guess what's next on the agenda? We know how to take care of the derivative in the case of addition. The derivative of the sum is the sum of the derivatives. Subtraction, multiplication. There's one thing missing. What do you do in the case of division? Well, we have to explore that. That will yield the quotient rule. We'll start by writing this as f of x over g of x prime. And the only thing we have to go on is the definition of the derivative. And that begins with the limit as h goes to 0. We're going to have f of x plus h minus divided by g of x plus h minus f of x over g of x all over h. At this point, we are subtracting. We are subtracting fractions. How do you subtract fractions? You have to have a common denominator, of course. So we'll write that as the limit as h goes to 0. Can we write this h as 1 over h out front for a moment? The rest of it is going to be f of x plus h times g of x minus f of x times g of x plus h all over g of x times g of x plus h. Yes, you'd have to multiply the first fraction by g of x over g of x, and the second fraction by g of x plus h over g of x plus h. And that yields this fraction right here. It's at this point that we need to do the add 0 trick again. We'll write this as the limit as h goes to 0 of 1 over h times the fraction f of x plus h g of x. Here's the term we're going to insert. F of x g of x plus the same, so it's not really going to change anything, and then minus f of x g of x plus h all over g of x plus h. Now we do need to suss this out a little bit. I'm going to switch these two factors in the denominator, g of x plus h. These will come out front. This will go inside. On the first two terms, we have a common factor of g of x. I'm going to factor that out on the right. On the second two terms, we have a common factor of f of x, but I'm not going to factor f of x out. I'm going to factor minus f of x out. That'll switch the order and give me g of x plus h minus g of x over h. Now, when we take the limit as h goes to 0, the first factor in the braces is f prime times g, and then we get minus f times g prime. These will still be in the denominator, but as h goes to 0, we get the following: f prime of x g of x minus f of x g prime of x over g of x quantity squared. The short form of the quotient rule is derivative of f over g is f prime g minus f g prime over g squared. One can also write that as the derivative of f of x over g of x is derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. Some people use a little sing-song phrase to try to remember this. They say low d high minus high d low over low squared. I don't really like that because students are always getting it backwards, screwing up the quotient rule. Subtraction is not commutative. You can't switch the order of the terms in the numerator. Instead, I'll have you remember it this way. The derivative of top over bottom is the derivative of the top, that goes first, times the bottom minus the top times the derivative of the bottom over the bottom squared. To this point in the development of our theory, we haven't been able to calculate the derivative of rational functions. What are rational functions? That's right. Rational functions are ratios of polynomials. Suppose I'm trying to calculate the derivative of 7x plus 2 over x squared plus 1. How do I do that? Now we know. You take the derivative of the top times the bottom left alone minus the top times the derivative of the bottom over the bottom squared. It's easy as that. You can see that we'll get a 7x squared. We also get a minus 14x squared. So that's a negative 7x squared. We'll get a plus 4x. And then we'll get plus 7. Still over the denominator squared. So far, the power rule has only been proved for in an element of the set of whole numbers. We've said that we would prove this for powers that are any real number. We can't do that yet, but what we can do is we can extend the result from before into the set of integers. That allows for negatives to come into the picture. The whole numbers only go from 0 up. For our proof, we only need to prove the case where n is an integer in negative, because the positive or 0 case has already been proved. Let's take the derivative then of x to the n. Well, what we'll do is we'll convert this problem that we have not proved to a problem that we can prove. I'll shove this across the division symbol. If n is negative, then negative n is positive. So we can take the derivative of that, but now it's in the denominator. The only way to calculate the derivative now, since this is a quotient, is to use the quotient rule. So by the quotient rule, we get the derivative of the top times the bottom, okay, that's 0, minus the top times the derivative of the bottom. The derivative of the bottom, we use the old style power rule. Bring power down, subtract 1 from the exponent, and that's all divided by bottom squared. Now, notice that on the top, first term is 0. We have minus minus. That's positive. We have x to the power of minus n minus 1, but the denominator is x to the minus 2n. And when you divide things having the same base, you subtract the exponents. So we're going to have minus n minus 1 minus negative 2n. Well, what is that? Minus minus is plus, 2n minus n is n, and we're left with minus 1. Now we've extended the power rule for all integers, but we still need to prove that it's true for things that are not integers as well in the set of real numbers. Now, we've calculated the derivative of the sine function. The derivative of sine is cosine. We've calculated the derivative of the cosine function. The derivative of cosine is minus sine. But there are 4 other trig functions to deal with. Let's look at the derivative of the tangent function. By the ratio identity, tangent is sine over cosine. After all, in proving many trig identities, one strategy is to convert everything to sines and cosines. We're going to do that for all 4 of these derivatives that remain for the trig functions. You can clearly see that since the tangent function is expressible as a quotient, its derivative requires the quotient rule. The derivative of the top is cosine times the bottom minus the top times the derivative of the bottom over the bottom squared. We have then, this is not the usual notation for cosine squared. We usually just write it as this. This notation means this sequence of operations, by the way. You need to understand that there's a mathematical convention about the trig functions that puts squares here instead of here. Minus minus is plus sine squared x over cosine squared x. Ooh, I have an idea. Can we cancel the cosine squared? No, you may not cancel from terms. What you can do is note that cosine squared x plus sine squared x is 1. Now, by another ratio identity, 1 over cosine is secant. So 1 over cosine squared is secant squared x. So we've shown that the derivative of tan x is secant squared x. I need you to memorize this right now. Well, that game should play out pretty much the same way when we calculate the derivative of cotangent. That's the derivative of cosine over sine. And again, that requires the quotient rule. Derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. Now the numerator has a common factor of minus 1. I'll factor that out. What is the name of the identity that sine squared x plus cosine squared x equals 1? That's called the Pythagorean identity. I like to give things their proper name. That beats pointing and grunting. Puts us a little bit above the caveman status. Most of us are not troglodytes. I might be, but you're not going to be one. -1 over sine squared x, that's negative cosecant squared x. We've just shown that the derivative of cotangent x is minus cosecant squared x. You need to memorize this right now. 4 down, 2 to go. Secant and cosecant are on the line up next. Derivative of secant, well, by a ratio identity, that's 1 over cosine x. And again, that's a quotient. We will apply the quotient rule. Derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. I'm going to split off 1 over cosine x, and the rest of it will be sine x over cosine x. 1 over cosine is secant. Sine over cosine is tangent, and don't leave the x's off. Don't get cheap with me. Put it in. We've just shown that the derivative of secant x is secant x tangent x. You guessed it. You need to memorize this. And then there was 1. Cosecant. Of course, the ratio identity is 1 over sine x, derivative of the top times the bottom, minus the top times the derivative of the bottom over the bottom squared. We have a minus. I'm going to factor out a 1 over sine x, and what's left is cosine x over sine x. We get minus cosecant x cotangent x. So we've just shown that the derivative of cosecant x is equal to minus cosecant x cotangent x. And of course, you're going to memorize that. But I'm going to make a table that will aid you in the memorization process. I'm going to make a table, and I want you to construct this table in exactly the same way. Exactly the same way. Don't be cheap. Don't try to do various abbreviations. Write out the whole table. We're going to begin with the derivative of sine x, which you know to be cosine x. To the right of that, I'm going to put the derivative of the cofunction cosine x, which you know to be minus sine x. Next, we have the derivative of the tangent function, which you know to be secant squared x. The derivative of the cotangent function is minus cosecant squared x. One more row. The derivative of secant x is secant x tangent x. The derivative of cosecant x is minus cosecant x cotangent x. I want you to notice the patterns here. Whenever we do the derivative of a cotrig function, we get a minus. And only on those cotrig function derivatives do you get a minus. If you have a function here and a trig function here, you'll have the co-trig functions on the other side. So memorizing the first column should give you immediately the second column. If you know that the derivative of secant is secant tangent, then the derivative of cosecant should be minus cosecant cotangent. You really do need to memorize these facts. They're going to be used throughout the other semesters of calculus. Some people decry rote memorization. I don't. Memorization takes place through the hippocampus, a region of the brain. To fail to memorize is to fail to exercise that portion of the brain. You hear people talk of higher order thinking skills and lower order thinking skills. That's nonsense. There are just different brain regions. I want to exercise the whole brain and leave no brain region underdeveloped. As an example, suppose y is equal to tangent of x minus x squared. By a mathematical convention, we may leave the parentheses off of the tangent function, and unless we put parentheses around the entire expression that's left, we intend that the parentheses only apply to the x. So this is just tangent of x. The derivative is secant squared x minus 2x. Suppose I'm taking the derivative of y equals 1 plus, say, sine x over cosine x. We can simplify this by, instead of doing the quotient rule now, we can divide this up into two fractions re-expressing the function as secant x plus tangent x. Then the derivative is secant x tangent x plus secant squared x. I need to give you the notation for higher order derivatives. Recall that velocity, which we'll denote by v, which is a function of time, is the time rate of change of the position function. The rate of change of position with respect to time is called velocity. Also, acceleration, which we can denote by a of t, is the time rate of change of the velocity function. Well, velocity is already a derivative of position. So how do we write the derivative of the derivative of position? We call that the second order derivative. There has to be a more compact notation. And the way that we're going to express this as is with respect to d squared over dt squared of s of t, two applications of the derivative operator d dt. This is in the Leibnizian notation. The Newtonian notation works a little differently. Newton would say that velocity is the time rate of change of position. He would have described that using a dot positioned directly over the variable. Acceleration is the time rate of change of velocity, and that's the second order time rate of change of position. So Newton would have described his second order derivative using two dots. Dots because he used the dot whenever he intended to describe a derivative with respect to time. If the derivative was with respect to a spatial variable, he would have used a prime. So the notation goes like this. If I have the derivative of a derivative, describe some function, I can either describe that by the Leibnizian d squared dx squared of f of x, or f prime prime of x, using the Newtonian notation. What if I have more than two derivatives? The time rate of change of acceleration is called the jerk. So the jerk is the derivative of the acceleration. By the way, it's that jerk that tosses you around on a roller coaster. If you were just experiencing a constant acceleration, it would push you back into your seat perhaps, or pull you forward if you're stopping, but you would have a constant force being pushed against you. It's the changing force, the changing acceleration, that tosses you around. It's also that changing acceleration which causes a lot of the wear and tear on engine parts. It's the jerk of those engine parts that causes a lot of that wear and tear. If I have a third order derivative, okay, we describe that with the Leibnizian notation d cubed over dx cubed of f of x, or in the Newtonian notation, you can either use 3 primes, though 3 or more primes becomes a little tedious and sometimes difficult to distinguish. So there's another notation that we will use describing the number of derivatives, and that is parentheses 3. Whenever a superscript is expressed in parentheses, it means that many derivatives. So if I have f with a superscript of 4 in parentheses, that means do 4 derivatives. You might remember a formula from physics. The height of an object that's just falling under the influence of gravity is equal to the initial height plus the initial velocity times time. Remember, after all, distance equals rate times time, minus 1/2 gt squared, where g is the acceleration due to gravity, minus because gravity goes down. The velocity function will be the time rate of change of height with respect to time, the derivative of y naught, and that's y naught, like it's all for naught, nothing. That's why this is called y naught. Y sub 0, that's y naught. Not NOT or KNOT, but NAUGHT. It's a constant initial height. Its derivative is 0. The initial velocity is also constant, so when we take the derivative with respect to t, the derivative of t with respect to t is 1. Here we have minus 1/2 g, which is a constant. The derivative of t squared is 2t. The 2's cancel, and the velocity is the initial velocity minus the acceleration due to gravity times time. This might be yet another formula that you might recall from physics. Since the acceleration is the time rate of change of velocity, that's going to be 0 minus g, and the derivative of t with respect to t is 1. So the acceleration is a constant minus g. Who is the person who discovered that acceleration due to gravity is constant? A lot of my students will respond, Newton. No, it happened a long time before Newton, within the same century. But this fact is due to Galileo. The fact that acceleration was constant and independent of mass, or the particular construction of the object in motion, was controversial in Galileo's day. In fact, his discovery contradicted thousands of years of prior thought. Aristotle had taught that objects have an inherent velocity. When released, they achieve that velocity instantly and move at that constant velocity. Aristotle also felt that one didn't need to appeal to particular experiments to arrive at physical truth. One could do that through pure reason. Galileo proved that was nonsense. He overthrew, by experiments rolling marbles down ramps, that objects move at a constant rate of acceleration, not constant rate of velocity. There's also that mythical experiment of him dropping lead balls having different masses off of the Leaning Tower of Pisa. It may not be true, but it sure sounds good. Let's do a simple example. Suppose that you're on top of the Anadarko building. Which is one of the tallest buildings, the tallest building in the Woodlands, Texas. It is 439 feet tall. Let's suppose you toss a ball up and then it falls. Let's suppose this ball is made of lead and it has negligible air resistance in its journey up and down into the pond, where it splashes and leaves a wake rippling across the pond. I want to know certain things. First of all, I'm going to give you that the height is equal to 439 feet plus, let's suppose you toss this up at 50 feet per second and it comes down. In this case, G is, since we're in English units, 32 feet per second squared. Our formula is 1/2 this, so we'll get 16 t squared. Now, how high does this rock or this ball of lead go? How high does it go? When it gets to the maximum height, the speed is 0. The speed, the velocity in this case, is 50 minus 32t. The velocity is going to be 0. It's going to stop rising and then go down when we set the velocity equal to 0. Moving things around, we get 50 over 32 measured in seconds. How high was the rock at that point? Heights plop out of the original function. 439 plus 50 times 50 over 32 minus 6 times 50 over 32 squared. My calculator gives me about 478 feet. I have another question. We have the velocity now. The question I have is, how fast is it going when it hits the water? In order to figure out how fast the lead ball is moving on impact with the water, we first need to figure out when the lead ball impacts the surface of the water. To find that out, that's when the height is 0. So we'll set y equal to 0. And solve this quadratic equation for t, the time. If we multiply through by a negative, we can write this with a positive leading coefficient in descending order. Do you remember the quadratic formula? It's embarrassing, but I have to do this to you. Do you know the quadratic formula song? If you're dealing with a quadratic equation, by the way, If you erase this 0 equals and just write ax squared plus bx plus c, that's not a quadratic equation, that's a quadratic polynomial. To be an equation, you have to have an equal sign and two expressions separated by the equal sign. The quadratic formula is x equals minus b plus or minus square root b squared minus 4ac all over 2a. All right, I know. How do you get it out of your ears? But we do these corny things so that you can remember these things. So for us, the time is minus b plus or minus square root b squared minus 4ac minus 439. Minus is plus, by the way. All over 2 times a. There we have it. We're going to have both a plus and a minus here. Only one of these times represents when the ball hits the water. And if you think about it, if I have 50 squared plus some positive stuff, when I take the square root, I'm going to have something bigger than 50. Subtracted from 50, that'll be negative. I don't want the negative time, because that's some time prior to when I threw the ball. I want the positive time, so it's going to be plus, not minus. What is that value of t? I want you to try to calculate this right now. Keep in mind, whenever a fraction is expressed in this form with a horizontal bar, there's an implied set of parentheses around the entire numerator and around the entire denominator. Make sure you put those in. I want you to do this calculation because I want you to be sure that you're following the order of operations agreement and pushing the correct sequence of buttons on your calculator. So many students get this wrong when I do this in class. I have them sit down and do it. I demand that they do this on their own with their own calculator, and that's because I want them to work out any bugs now. I get 7.0286600101. Okay, well, let's just say 7 seconds. Do you get that? From the time the ball is released until it hits the water, 7 seconds will elapse. So, to answer the original question, how fast is the object going on impact? We have to plug in that 7 seconds into the velocity function. What do you get? I get minus 175-ish. What are the units of this answer? This is a velocity. This is going to be in feet per second. Suppose I want to know in miles per hour and not feet per second. By the way, negative because it was going down. There is a way to deal with this. We use the factor label method. 5,280 feet is 1 mile, and 3,600 seconds is 1 hour. Second units cancel, the feet units cancel. I'm left with miles per hour. How many miles per hour is the object going when it hits the water? The answer is 119.26 miles per hour. You definitely don't want to be down here on a boat when that thing comes flying through. To recap a part of today's lecture, we talked about the product rule and the quotient rule. You already know some other rules. The power rule, the derivative of the sum is the sum of the derivatives. The derivative of a constant times a function is a constant times the derivative of the function, the linearity properties. But there is one more important rule to learn. We'll do that in our next lecture.